I'm Zoë Fisher and I am a scientist at the ESS. I was a scientist at Los Alamos National Lab, and there my job was very much running a beamline and a support lab, to where now at ESS I get to lead a deuteration and crystallization support lab. One of my bigger, longer term projects involves enzyme carbonic anhydrase. So it's the same enzyme that does this really fast proton transfer in the human body, but one of the isoforms or cousins of this family of enzymes is only made in solid tumors. So there is a push to think about or find new ways of making isoform-specific inhibitors that bind to this cancer-related CA very, very strongly, but maybe binds poorly or not at all to the others. So you can have a more selective way of finding and treating metastatic tumors. I was definitely a solid X-ray crystallographer back in the day, but after years of studying very high-resolution crystal structures with X-rays of this enzyme system, it became apparent that the final piece of the puzzle I was not going to get with X-rays only. So I was at a conference as a graduate student, and a scientist came up and looked at my poster, and I briefly discussed sort of the issues I was having with this data, and he just casually threw out, "Oh, you should, consider doing a neutron experiment." We were always missing this little bit of information on where the waters are and how we can see the hydrogen bonds in and around the enzyme active site that we know are really important for the activity of this particular enzyme. And that's where neutrons come in. X-rays are the workhorse of this kind of investigation, where you're looking at large libraries of ligands binding to this particular target. That's one way to do it. We are saying all these drugs binding to this particular enzyme are doing it through interactions involving hydrogen atoms. They may do it through water-mediated hydrogen bonds. These compounds often make direct hydrogen bonds. And then, depending on the kinds of residues you have in the active site, these residues may be charged, they may be neutral, they can be positive or negatively charged, and how they appear electrostatically to a compound will very much determine how it binds. X-rays don't give you that layer of information. So we get high resolution, really beautiful, powerful information on the heavier atoms. But all these light atoms that are mediating these bonds between a ligand or inhibitor and a target, we need neutrons really to see these light atoms. So we never can do neutrons without X-rays. We need the high resolution data on the heavy atoms, but neutrons really become indispensable for looking at these ligand binding studies in particular. The next sort of revolution, I think, is going to involve membrane proteins. Nobody has yet done a neutron structure of a membrane protein because they are difficult to crystallize and grow big crystals, and often they have large unit cells, crystallographic unit cells, which make them not at all feasible for existing instruments. But again, the ESS, with amazing foresight, is planning for the NMX beamline to actually have the appropriate geometry to be able to do smaller crystals and much bigger unit cells. So we, on the DMX side, have to now really work to make labeled membrane proteins and also get the crystal size up there by at least one order of magnitude for what is common today to make it feasible for ESS.